Hi, everyone. Welcome to your first section in 2370 Elementary Analysis 1. I'm so happy you are here, and I'm really looking forward to this semester with you guys. So we're going to get right into it. I'm going to, first of all, again, just welcome. So excited you are here. I hope that you guys find that this course is useful and helpful to your future endeavors. So I'm looking forward to reading in the discussion board exactly what you guys are teaching so I can kind of focus and aim. I know that it is a math course, so we will be focusing on math, and what I'll try to do is, incorporate some best practices, some strategies, some things like that into the course as well that you wouldn't get in just a pure mathematics course. So today, we kind of just introduce the class. We want to just talk about what are some basic expectations from you guys. So basically, since this is an online course, all of your lectures, everything will be posted through Blackboard. All of the homework will be posted through WebAssign. And yes, most of the time the homework is going to look like, math homework. And then there will be room for discussion and sharing some of those teaching strategies and, like I said, best practices. Your first assignment is not due until September 2nd. So that gives you guys some time to get acquainted, get your textbook, and all of that good stuff. So when I give you guys the video lectures, it's going to cover some of the main ideas of that section, but it is always best, just like in any course, to read that chapter before you open the lecture. That will give you some background knowledge on where I'm coming from. And again, I'm just pointing out like those major hot topics in the section, but it is always best to read that on your own. And they're not so long. Those sections, they're actually pretty digestible. So I really suggest that as you guys are getting ready. Okay, so our first section, which is a major topic in this course, is going to be over problem solving strategies or just, problem solving. So George Polya was a really cool mathematician. And not only that, but he kind of dove into the how and the why, and not just the let's get some answers and let's prove mathematics, but it was thinking about the thinking, which is so important when we're teaching children. Um, it's not just about, here's a cool topic, learn it, answer it, take the test, pass it, and we're good. Has the student actually learned if they've never learned to think? And so no matter what course you're planning on teaching in the future, if it is math, wonderful. If it is not math, also wonderful. But either way, we are teaching students how to think. So any type of problem solving strategy will be crucial to those students. So in math in particular, this is what George Polya, sorry, came up with as some of those strategies. So the first thing is to read the problem. And that seems so basic, but it will be surprising to you how many people will try to get away with working a problem without reading it. So the first thing, I would usually ask my students is, what is the problem asking you to find? Like, what are you looking for? And if they can answer that, then they've checked off, I read the problem. Number two, then they have to come up with a plan. So problem solving strategies can look so different. It's basically just that roadmap from how are we going to get from point A to point B. And I always like to give an analogy is like, okay, guys, if we were about to go to the mall, how are we going to get there? And some kids like, we're going to take the loop, we're going to take 50th, we're going to run through buildings because they're middle schoolers and they're awesome. So you're like, okay, all of that being said, will we still get to the same answer? Yes. Okay, then all of your strategies are great. So really emphasize that there are more than one ways to get to the problem. So number three, carrying out that plan and solving the problem, modeling their thinking. So if it's not in a math course that you're thinking about problem solving, students can still model their thinking in Freyer models, graphic organizers, timelines, um, in math, number lines. There's a lot of different ways that they can prove their thinking. And then ultimately, what we want students to achieve is to be able to look back and examine their own results. So reasonableness is huge. Can they justify that their answer is reasonable? And by that, in math, obviously, if we're doing something like counting the number of rabbits on a farm and they end up with a negative answer, then they should quickly be able to go, wait a minute, I did something wrong here, and check themselves and be able to go back through the process and say, did I mess up when I read the problem? Did I mess up when I made my plan? Is it something in my calculations? And if we can get students to get there, then not only are we making that an easier process for us because students can check their work before their hands go up, um, but also it's making it an easier process on them and making them a better thinker. It would be great if all of our students could make 100s, but if we never actually taught the student how to think on their own, then are they truly getting a valuable experience from our classroom? So, again, there are similar examples in your book to these problems, but these are just some different problems, but using the same strategies that the book talks about. So, one of the strategies that the book says is that we want to teach students to look for patterns. And again, if they can do this in the real world, then we're making great adults for the future. um, so, in your book, this looks like Pascal's triangle, and it goes through all of that. And here, what we've got is a different triangle where we have a pattern where every row begins and ends with the two. So, what we have to do is to figure out what the pattern is. And not only that, but we're going to figure out what row 6 would look like here. Okay, so what I notice is I have a 2 and then 2. So those first two rows really don't tell me much. But then I get to row 3 and I'm like, oh, I've got a 4. Okay, so I've read my problem. I know what I'm being asked to find. Now I've got to figure out how to get there. So if I'm not really sure how to model my thinking here, I can go off to the side and just start inferring what might be happening. So I notice that 4 has a relationship with 2 and 2, and I could start modeling my thinking by going, is it 2 plus 2? That gives me 4. Or is it 2 times 2? That also gives me 4. So I don't know yet. So I'm going to go to row 4. So I've had to go down 4 rows to possibly find a pattern. And I'm looking at this and going, 8. Okay, that has a relationship with 2 and 4. Oh, and the other 8 has a relationship with 2 and 4. So I may have found my pattern here. I think that I am multiplying the two numbers that are right above my number to get my answer. So that checks out because 2 times 4 is 8, which means my addition hypothesis there is not correct, but it helped me to get to the correct answer. So I'll check it again because, of course, I want to make sure that this works. So 2 times 8 is 16. Yes. 8 times 8 is 64. And 8 times 2 is 16. So now I know how to find row 6 if I continue. So before I do that, I want to write a description of what is even happening. So here's what we basically said. To get the values in the next row, we multiply the two numbers in the row above. And we could add more to that. We could say adjacent. We could say to the corners that are touching. Put that in whatever language that makes sense. But now we at least know what the pattern is doing. All right, let's find row 6. So for row 6, I know that the first and the last numbers are going to be 2. I also know that each of these is basically um, the number of numbers is the same as the row number. So in row 5, I had 1, 2, 3, 4, 5. So I'm going to have 6 numbers in row 6. 2, 5. Let's make enough room there. There we go. So I already said the first and the last number will be 2. And then here's my job. I've got to find what those adjacent numbers would be. So the first one shouldn't be too bad. 2 times 16 is 32. And then I've got 16 times 64. So we multiply that together and we get 1024. And this one was nice to us. It gave us the same problem again, so I don't have to multiply that again. 1024. And then, oh, there's my pattern. So it's going to end with the first number that I got when I multiplied 2 times 16. So that is row 6. And I figured out how this pattern was working. Okay. Our second problem-solving strategy in chapter 1 is to read or make a graph. So here we've got the number of customers. So they're telling us that each little guy is 100 people, and we have this modeled by days of the week. So what I can do here is I can just think about visually what I am seeing. What I am seeing is that there are less people on Monday, Tuesday, Wednesday, Thursday. And then after that, it looks like it spikes a little bit on Saturday. And then after Sunday, it just decreases. So here, all I'm being asked to do is to describe. And my description is going to be, pretty simple. Let me go back. I can. Oh, there we are. Sorry, guys. Um, and all I'm going to say here is basically that the number of customers increases Monday through Saturday, then decreases. So sometimes we don't need to necessarily find the answer or look for a specific number. We're just describing what that pattern is doing. Okay. And then our last example here, we're going to make a table. So first thing I've got to do is read my problem, figuring out what I'm going to find. So it says a frog is climbing out of a well that is 23 feet deep. The frog can climb 3 feet per hour, but then it rests for an hour, during which it slips back 2 feet. How long will it take for the frog to get out of the well? So if you notice that, I'm annotating as I'm reading. And I really love to tell students to do that because they forget, especially nowadays with so much being online. If there is a platform that they can use to annotate, to kind of dig into their reading, then that is better, I think. Okay, so first things first, what is it asking me to find? I'm trying to figure out how long it will take. So by that, I'm looking for the time, and the time here is being written in hours. So my answer is going to be something written in hours. Okay, now how am I going to get there? I'm a very visual person, and that's why tables and graphs are awesome. So what I'm going to do here is I'm going to make a table, and I'm going to show the relationship in the number of hours and the height. And our height was in feet. And I'm just going to go through this one by one. So in hour 1, he would have climbed up 3 feet. In hour 2, he's going to slip back 2 feet because remember he rests. So this is going to actually I'm going to subtract 2, so I get 1. So here I notice I took away 2. And then the next hour, hour 3, he's going to continue to go up again. So I end up with 4. And then hour 4, this is when he drops down again. And I get 2. So I keep going. I've got 5. 5, I get adding 3 again. So get 5. 6, I'm subtracting 2 again. And I get 3. Okay, we're going to figure this out without having to write them all out because that's a lot. What I notice is that I see a pattern going on with some of these numbers. I don't know if you guys kind of see, but in my even numbers, I am basically counting like 1, 2, 3. Okay, so if I continued that pattern and I went up all the even numbers and I just counted consecutively, when I get to 40, I will end up at the 20th, or sorry, 20 feet. So if I can get that far, remember I'm trying to get to 23. And if I notice that my patterns were always adding after my even numbers, so what I did is I followed my even numbers, then I can add 3 and I end up at 23 when I get to 41. So it will take him 41 hours to get to 23 feet. Granted, this one is going to be a little bit harder to explain algebraically because you don't have a constant rate of change. So we can't express it linearly. Um, it's not multiplicative, so it can't be exponential. You've got this crazy, you're switching the pattern back and forth. So that is why I chose to look at a sequence of numbers, especially just looking at all of our even numbers and seeing what kind of pattern is going on there. So we found our answer. It will take the frog 41 hours to get out of the well. And then we check, does that seem reasonable? I think so, especially because he is having to slip back every other hour and then go up and then slip back and go up. So this does make sense. And this is definitely one of those problems where you may give it to a class of students and you've got 3 or 4 different methods going on in your class. Again, how we get to the mall is going to be different depending on the person. But as long as we all end up in the same place, that is valuable. So even if I was going through this problem and you were sitting there and you saw a pattern right away, again, take that to the discussion board, share it out with us, tell us how you would do this. You're more than welcome to share pictures on there as well if you want to show us your modeling and your reasoning. That is what this class is all about. So